Nanotechnology applications in solar energy. What is nano? Nano is a prefix used to describe 1/billionth of whatever follows. For example, 1 nanometer is equal to 1/billionth of a meter. To give you an example of just how small this is, we have depicted the human hair. The human hair ranges from 50 to 100,000 nanometers in diameter. For nanotechnology, the typical nano ranges from 1 nanometer, the width of DNA, to 100 nanometers, the size of the flu virus. It's important to note that this is a typical range. Larger values can be accepted if the material exhibits unique properties due to its small size. The first of these effects is the surface area to volume ratio. Take, for example, 3 boxes of the same volume. The first box remains whole, with 100 centimeter by 100 centimeter faces. This is the surface area. The second box gets cut up into 8 smaller cubes, with 50 centimeter by 50 centimeter faces. The third box gets cut up into 64 smaller cubes, with 25 centimeter by 25 centimeter faces. As you can see, the surface area of the second box doubles that of the first, and by the time we make it to the third box, the surface area has quadrupled that of the first, while maintaining the same overall volume. Imagine how large the surface area would be if the first box were cut up into 10 to the 27 smaller cubes, resulting in 1 nanometer by 1 nanometer faces. This large surface area would allow more of the material to interact with its environment.
The second nano effect is quantum confinement. In bulk material, electrons are able to move through relatively large spaces. In nanomaterial, electrons are confined to extremely small spaces, sometimes only a few atoms in size. This confinement causes a quantization of energy, where electrons can only exist in specific energy levels. This can be modeled by the following diagrams. Here is a visual representation of the number of energy levels in which electrons can exist, where the gaps represent the energy required for electron movement. Notice that we can adjust this energy by adjusting the size of the particles.
Now that we've discussed the nano effects on materials, let's explore a specific application, thin film solar panels. But first, let's briefly describe how solar panels work. A typical solar panel harnesses energy from the sun to produce electricity. Once light hits the panel, electrons inside the material are excited and a current is produced. This current is then collected using a network of thin conductive strips on the surface of the panel. The collected current can then be stored or sent directly to a specific application.
How are nano effects used in thin film solar panels? As seen earlier with quantum confinement, we can adjust this gap, the energy for electron movement, of the material being used in the thin film to ensure that the optimum energy wavelengths are being absorbed. Another way to adjust which wavelengths are absorbed is to add nanostructured pillars to the surface of the thin film.
With these developments in solar technology at the nanoscale, there are many future possibilities for large-scale applications. Using the highly conductive properties of certain nanomaterials can improve the efficiency of thin film solar panels. For example, graphene is a single layer of carbon atoms that can be transparent. This material has the potential to improve the efficiency of thin film solar by improving panel-to-light contact and electrical current collection. Some applications of these high-efficiency thin films include, in the near future, portable laptop chargers that roll up for storage, and eventually, in the distant future, assisting spaceships with interplanetary travel.